We're going to use exercise 1069 of Montgomery and Runger as a classic example of the difference in population proportions and the hypothesis tests that come out of those. In engineering practice, we of course are going to be looking at something different, perhaps defect rates between two different populations and whether or not there's a significant difference between those, assuming that we're not talking about real rare kinds of defects. Alright, so let's dig into this first by actually going back to the past and talk about the tests that we had for proportion that were for a single sample first, and then bring that forward to the future as we look at differences in proportions. And remember, we're really talking about this binary world of being able to classify, lump everything on one side or the other side. And that led us to this binomial parameter p, this fraction of whichever was of interest that we wanted to take a look at. One particularly important aspect here for this application back for single samples was that we had large sample size and the success or failure likelihood was not too close to 0, 1. So we were not looking at rare outcomes. We have other models that are more appropriate when we're looking at exceptionally rare type outcomes. So 0.001 or even smaller, 10 to the minus fourth, that sort of number is not the kind of defect rate that we're looking at in this kind of example. Right? And we were led to a normal approximation here, and here is our key for the limits for that approximation, n times p or n times q being greater than 5. Our estimator for that fraction was just simple the number in that class divided by the number in the sample. That was our point estimate, and then the sampling distribution became normal with the estimated, or rather the expected value of our estimator being equal to our true population value, and then the variance, right, not standard deviation, but variance was PQ over N, leading to a test statistic here for Z approximate normal x minus n times p naught over square root of n PQ. Okay, that was for a single sample, and we're going to bring that forward now to talk about this for two samples. So here, this is election results back from 2004 from Ohio, where respondents with college degrees, 53% voted for Bush, 1071, 930 voted for Kerry out of 2020 respondents. And we're asking two different questions, one about a statistically significant difference between those two proportions, and then also a confidence interval between those two. And we'll kind of go after those two, develop the work first generally per se, and then we'll get into the specific numbers for this particular case. All right, so let's start at the very beginning with our background. This will be way more than we need just to answer the specific question, but it'll lead to the simplified approach that we're going to use. Right? Our null hypothesis here is typically going to be that the two proportions are the same, and of course the alternative is that they're not. So it's a two-sided test. Okay, and our population proportions, P, well, that's just equal to x1 over n1, and P2 would be x2 over n2, where the x is the number of, quote, success for that class, the number in that class. Right, now we'll talk about the pool situation that we're going to have here in a moment, but right now these are two different random samples, two independent samples of two different sizes taken from two different populations. Okay. And that leads us then to the test statistic that's really going to look the same as what we've been working with, the same pattern. The symbol that we use is somewhat arbitrary in the sense it could be any, we could have just called it a statistic, such as like a theta, but we change it depending upon our understanding of what the sampling distribution is going to end up being. And so the fact that we're going to call this z already tells you that we're going to be looking at this as somehow a normal distribution, right? And if we're looking at differences here, then we're going to take a look at the difference between the two measured out of our sample, P1 minus P2, and then minus the expected value of that. So that would be the actual P1 minus P2. Right, this is general right now. Under this hypothesis test, of course, this would be 0 because we're testing that those are the same. Right, we'll simplify that here in a moment. And then we'll divide by a standard deviation. And in this case, then it's P1 times 1 minus P1 over N1 plus P2 times 1 minus P2 over N2. Right, well, the problem, of course, is that we don't know these guys, right? And we're testing to see if they're the same, but we don't actually know them. So this is a fine test statistic, but we need to modify, work with it here just a little bit. And so under our null hypothesis, then P1 equals P2, and we'll let that then just be the symbol P. Right? And our estimator for P then is of course going to be associated with P hat, and coming out of two different populations. Right? So our test statistic changed a little bit here. This is going to be P1 hat minus P2 hat, and then this becomes 0. Right? And then in the denominator and under the radical, these became the same p-values, so we'll factor those out, times 1 over N1 plus 1 over N2. Right? And we could leave that, except for we still have the issue that, well, gee, but wait a minute, what are those? We don't know what those are yet either. And so what we're going to do is we're going to also say for a pooled proportion is going to be equal to x1 plus x2 over n1 plus n2. Okay, and so now that's a little different, and we're going to move away from something that was strictly normal to something now that's just approximately normal, because we've transformed this, changed this a little bit. And that's a key thing to keep track of, that we've now made a slight change there. Right. Okay, so we'll substitute in our test statistic will be P1 hat minus P2 hat all over square root of P hat 1 minus P hat. Some people again like to use Q here just to keep this a little simpler. And we have 1 over N1 plus 1 over N2 as our test statistic. And then that's going to be interpreted in the same kind of way that we've done for all of our other tests that we've done, processed and done in a similar kind of way using the normal curve. So let's go back and work with our production team. There's going to be a pause here. I need to blow my nose and need you to cut that out. Okay, so we're going to work with that test statistic and go back to our numbers here for this example and come up first with the hypothesis test, and then we'll do the confidence interval. Right, so for part A, for step 1, the parameters of interest are going to be P1, we'll call that the Bush proportion, and P2 will be the Carey proportion. Right? And so our null hypothesis goes back to same thing, P1 equal to P2, and the alternative hypothesis being that they're not equal to each other. So two-sided. Our significance level is 0.05. Right, and so that means right away we know the Z alpha over 2 is going to be equal to plus or minus 1.96. I use that a lot, so we know that number is right there. Our test statistic then is Z0 equals P1 hat minus P2 hat over square root of P hat, that's the pooled, minus P hat, the pooled, times 1 over N1 plus 1 over N2. Okay, and our, we won't calculate that just yet. Let's also put this off to the side here, that P hat is equal to X1 plus X2, that's the pooled, N1 plus N2. And so let's state our rejection rule, or operating rule. We're going to reject H0 if our Z0 that we calculate is less than minus 1.96, or Z0 is greater than 1.96. And that's from our 0.05 confidence level. Right, so now let's get down to some calculations. And there are a couple little wrinkles that are a little bit different than they are in the example you see in the textbook. Right? So N1 equals 2020, our X1 equaled 1071, and our P hat 1 was 53%. And then the second one equals 2020, X2 equaled 930, and our P hat 2 equaled 0.46. Now, the reason why I say this is a little bit different is that in your example in the book, they talk about a placebo effect in a specific medical remedy, and so they had a population size, or sample size really, of 200 that got divided into equal halves, 100 and 100, and placebo versus the medical remedy. Right? And this is a little different because we're actually only polling 2020, and we're going to treat that 2020 twice and get two different proportions, add up the proportions. They're not supposed to all equal to 1. There's another fraction out there that might have done something other than these two particular candidates. And it's a little goofy because it's not so clear to me, for instance, that these are two absolutely independent samples, and that's a criteria of how we develop this model. It's fairly common to do this approach, but it's not quite as pristine as what I personally would be comfortable with. But it is common in the polling industry to treat the numbers this way. At least that's my understanding. Okay, So a little goofy, and not quite the same as what we might do in the medical industry for that context, or for the context of some of what we do in engineering. It's a little bit different. Right, so our p hat, our pooled estimator, not sub 1 or sub 2, but the pooled, is going to be the sum of these two, 1071 plus 930 over 2020 plus 2020. Again, it illustrates that we're treating this 2020 set of respondents in a sense sort of twice. And we're really, in this approach, ending up with an average, in essence, between those two pools of respondents. So 0.495 tells us that, yeah, we did have nearly all of the population, 99% of the population voted for one of the two candidates, right? And so our z-value here, plug in the numbers, and 0.53 minus 0.46 over the square root of 0.495 times 1 minus 0.495, right? And then 1 over 2020 plus 1 over 2020, all square root. And that gives us a z-naught value of 4.45. Right, so we look at our rule here, that exceeds our criteria, so therefore we reject H naught at the 5% significance level and conclude that there is a significant difference at that 5% significant level between those two proportions. Okay, and note, if we wanted to go calculate a p-value, we could. That's going to equal 2 times 1 minus the probability that z is less than 4.45. That was our z-naught value. Right, this is one tail, and it's a two-tail thing, so that's why the 2. And of course, that's exceptionally small. It's darn near close to 0. Okay, and then for the confidence interval, the development work is in your text, and I'll let you take a look at that. Our upper and lower bound here, there's your difference minus our z alpha value, and then one of them will be plus, one of them will be minus, and then we're just taking that sigma value, and so that's p hat 1, 1 minus p hat 1 over n1 plus p hat 2, 1 minus p hat 2 over n2. All right, and we'll end up with, when we do all that, that we will have a 0.039 less than equal p1 minus p2 less than or equal to about 0.1 when we process that all the way through. Right? And so that interval does not contain 0. And so therefore, based on confidence interval, we would conclude that there's a significant difference in the proportions. We'd also conclude that, of course, up here as well, that there's a significant difference. So we have two different tests, both of them concluding the same thing. Of course, there's a relationship between these two, but it's not always going to be exactly identical, right? So it's good to see that we have two different tests that give us the same kind of conclusion. What you'll see in your textbook in greater detail are the type 2 error and choice of sample size calculations. The equations look long. They're ultimately actually fairly straightforward, and I'll let you take a look at those on your own time as interest is there and as the situation or practical standpoint arises.